Alright, so now we're looking at question 2, which is the same problem as question 1. The only difference is we're going to get our properties on this pH diagram. So just a few of the things on this pH diagram. Here's the compressed liquid line. Comes all the way up here to the critical point. Then it becomes the saturated vapor line. Not sure if I said that right. Saturated liquid all the way over here. Saturated vapor goes this way. And then comes down here. My pen's not working, but you can see the path that I'm taking. Switch colors here. The y-axis is pressure. That's in bar. 1 bar is 100 kilopascals. The x-axis is enthalpy in kilojoules per kilogram. So the first point that we had was 100 kilopascals, so 1 bar, and saturated vapor. That's point 1 that we got in the tables. On the pH diagram, this is the saturated vapor line. Here's the pressure of 1 bar, so that is right there. We can get a few properties from there. One is we can get the enthalpy. So go straight down. Here you see that enthalpy is 380. Here's 400, so it's 382, plus or minus a couple. Another thing that we can see are temperatures. So temperatures, you come down over here. Here's the line for -20. Here's a line for -30. These go straight across at constant pressure through saturation. So this -20 meets up with this -20, and then it curves down this way. So for example, here's 60 degrees, comes straight across to 60 degrees, and then 60 degrees curves out this way. And then one more time at the bottom here, they tell you that it's 60 degrees. Okay, so there was point 1. Lines of constant entropy. Here's S equals 1.75, S equals 1.8, 1.85. So we're going to go parallel to those lines because it's isentropic from 1 to 2. And we're going to go up until our pressure reaches 1400 kilopascals, which would be 14 bar. This is a log scale over here, so it's pretty tough to tell exactly where 14 is going to be. Here's 1 and 10. There's 10 and 20, so 14 is going to be somewhere about halfway, maybe slightly higher than halfway. So we're at this intersection, this constant entropy and the pressure of 14 bar. So if I say 14 bar is about here, there's where the entropy matches point 1 and the pressure matches my pressure at 14 bar. So let's see if I can write a 2 upside down. I'm going to write it this way so I don't mess it up. Okay, so now we have points 1 and 2. We cool from 2 straight across at constant pressure till we have saturated liquid at 3. Hopefully I wrote that 3 correctly. Oh, I wrote it backwards. That's what happens when you write upside down. There's 3. Make sure I have my paper centered here. And then constant enthalpy from 3 to 4. Straight down. Constant pressure from 4 to 1. So that would complete the cycle. So some of the properties. We got enthalpy 1 and we got temperature 1. State 2 we see out here in the superheated region. Here's the line of 60 degrees. Here's the line of 70 degrees. So we can see this point falls between 60 and 70 degrees. Looks like it's closer to 60. So we call temperature 2, say 63 degrees. The enthalpy at 2 looks like it's just slightly less than this enthalpy. Come straight down, there's 420 and there's 440. It's slightly less than 440, so call it 435, 436. Something like that for enthalpy 2. Enthalpy 3, see these two go straight down. Those are 260 and 280. Or closer to 80 than 260, so it's 270, say 272, 273, 274, something like that. For enthalpy at 3 and 4, same enthalpy. Looks like the temperature at 3 is slightly higher than 50 degrees. There's where 50 hits, there's where 60 hits, so 51 or 52 degrees. Come down here to 0.4, and it's a saturated mixture at 100 kilopascals. So over here we see the saturation temperature is between -20 and -30. -30 is down there, -20 is here. So, I don't know, -26 degrees, -27 degrees, something like that. Both at 0.4 and 0.1 is also -27 degrees or so, because it was saturated at both of those points. Saturated mixture here, saturated vapor here, at the same pressure. So they have to be the same temperature. So there's all your enthalpies, temperatures. Here's how we used entropy. Those are the main things that you can get off a pH diagram. So then you put all these into the same equations as problem 1, and you should get the same results. One key thing to notice here, the temperatures should agree. What may not agree is the enthalpies, because enthalpy is a relative property. So someone just decided that enthalpy of 0 was something, and then everything else is measured with respect to that. So you're always doing a difference in enthalpy. And so it doesn't have to agree with the tables, but the results that you get should agree. So say the mass flow rate, or the rate of power consumed by the compressor, or heat rejected from the condenser, coefficient of performance. Those things should all agree. The enthalpy itself may not agree. The differences will, though.